Today we are going to continue where we left off with interpreters, and we're going to look at monadic interpreters. So I've copied the code from last week. It's exactly the same. And we're going to make this monadic. So first of all, I'm going to tell you why. And it's kind of, what is the point of these aggressively strongly typed languages? What is the point of having such an expressive type system? The point is, so we can make, first of all, we can make adding features really easy. Because just like with the monad, where we looked at sort of doing error handling, but in types, we weren't just passing bools around and doing constant checks like in other languages. We were making a monad, and we are using monadic bind to handle errors. It's like that. We can add features really easily and in really transparent ways, and it just makes our code less complicated. We kind of get to a level of complexity, and then the complexity just stops. We can offload complexity to the type programming. So that's one reason. The other reason is pushing your code into more and more and more type stuff, in my opinion, is always a good idea. And that's because I hate bugs so much. And I'm sure you do too. You have to. You're a programmer. Of course you hate bugs. And I think a good Haskell programmer is thinking about how they can make as little code compile as possible. Not trying to get their code to compile. You shouldn't feel like you're fighting the compiler, the type checker. You might do now, because you're quite new to Haskell maybe. And that's okay. But as you get more used to the type system, you shouldn't feel like you're fighting it. You should feel like it's helping you. You should be making your code so that there's only really, the ideal is that there's only really one function implementation that will fit the type. And then you kind of know your code is gonna work. If it passes the type checker, your type checker has proven that code, on the assumption that there's only one function that could fit the type, it's proven that it's correct. You can kind of get the type checker to do proofs for you in that respect. So it's always a good idea to push things to the type level. And we can do a lot more than we're ever going to cover in this tutorial. You can make interpreters that are type sound by construction, just by making the types a little bit more complicated. It's almost like you're doing more computation in the type level than not in the type level. And that means that the Haskell type checker is proving soundness for you, and that's quite incredible. But anyway, we're looking more at the first. We're adding features through types. That's what we're looking at. And I think I'm going to go about this. Let's go about this the really easy way. What we're going to do is we're going to define a monad. And it's a really easy monad. I'm just going to call it I. And it's going to equal IA. It's probably the easiest. It's the easiest type you've ever seen. And this is the identity monad. Maybe I'll make it slightly IDA for identity. I could probably... No, I'm not going to do that. Okay, so... Yeah, well, I'll say, if we weren't using Haskell types, if we were kind of not using type classes, then I would define it like this. But we're sticking to Haskell type classes, so we're going to have to define instances for functor. Yep. And we're going to have to define instances for applicative. And we're going to have to define a monad instance. So we'll start with functor. So functor, we say ID is a functor. So if you remember, this is the type for fmap, brackets, A to B to FA to FB. So fmap is a really easy one to define. They're all quite easy for this. We have our function, f. We have something of type IDA. Pattern match out, call it X. Just X seems like a nicer letter. And we're going to return ID f of X. That's it for fmap. Very easy. So next, applicative. So if you remember, we have two functions. We have this infix sort of apply infix. I feel like it shouldn't be called apply. I don't really know how I'd say that symbol, but I'll call it app. So this is the type for that one, functor, f, and it's f a to b on the left of it, and then on the right of it we have an fa and an fb afterwards. So let's define it. No, I'm not going to do it infix. So very easy. We have our function, which we just pattern match out, app, and then we have our first value, id x, and we return id f of x. Nice and easy, but there's also pure. So if you remember, pure, I'm not going to say it's f as a functor. F as a functor is just a to f of a. That's the type of pure. It's very easy. F of x equals id x. Perfect, we've got those two definitions down. Next is monad. So this one's nice and easy as well. So we define bind. I'll give you the definition of bind again. So here, monad m, we have ma to a to mb to mb. Really, it's writing itself because it's just id x bound to f equals f of x. That's it, and we're good. We've given a full definition of why id is a monad. So let's close this and see if we had any errors. Yes, I've missed an N. Yeah, don't pronounce that. Functor. Oops. There we go. So we now have, it looked wrong, but I couldn't quite put my finger on why. There we go. Lovely. So now that we have our seemingly pointless monad, and it is seemingly pointless, we are going to make a type alias for it for now, and we are going to try and make our interpreter monadic. And we're going to do that by sticking an M there. We're going to have to make a lot more changes, but that's the first change. So everything now is of the wrong type, and we're going to have to go through every single case of this function and change it. So numval I is of type value, so we are going to return it. Oh, nice and easy. Same with boolval. We're going to return it. So with this though, this is of type m value. This is of type m value. So is there anything clever we can do here? I think there is. So if I say equals equals, that is of type odd to bool. So if I f map over it something of type m value, the result is of type m value odd to bool. So then if I apply this, that whole thing now is going to be of type m bool. So all I should need to do is wrap it in some more brackets, because I don't want to think about precedence right now. And I should be able to go boolval like that. Now that might be wrong. We're going to find out. If it's not wrong, that's nice and elegant, and I'll be pretty happy with that. We can kind of do the same here. I don't know why I'm so determined to do everything in a really applicative way today, but I am. So it's going to be plus. Oh no, this isn't going to work this way because we need to pattern match on numval. So how I'm going to do this one is with the do monad. So it's very easy to turn let expressions into do notation. So I'm going to do that just to, it's the path of least resistance, I think. So that's that done. This can happen, yep, exactly the same. Do I want to write it like this? Yeah. I always think it's a bit, I don't like the indentation using do notation like this. Because what you can do is you can do it like this. Maybe I'll do it like this. I think it just looks a little bit nicer, but many might disagree with me. I think it's just, yeah, I'll do it like that. Okay, anyway, I need to stop talking to myself because I'm recording. Some people don't know that that do notation has semicolons. And I think it's one of Haskell's better kept secrets, because then it just feels too much like imperative programming for some. But I get around that by putting the semicolons at the beginning of a new line instead of at the end. Anyway, enough talking. I'm going to leave this line for now. No, I won't. Find. So find, in the environment doesn't have monadic values in it. So I see absolutely no reason that we should make find monadic. So I'm going to return find. Cool. I will leave that one for now though, because elab is definitely going to become monadic. Closures are nice and easy. That's a return. This one's nice and easy as well. So we can just bind this to a lambda, give it a name, R, and then we can do case of R. And then do we need to change? Nope, these are all fine because a val is monadic already. Cool. Apply last. Okay, apply is another. So apply is just an eval. So let's change that to an M. So that's all good, but we do quite a bit of mapping here. So first of all, map M. We're going to use map M. So the difference between map and map M is how it deals with monads. So say I just use plain old map with a, I'll just show you on the REPL. This is going to error. Okay. It has errored, but for a reason I didn't foresee. I need to go change that. Anyway, map. You know what that is. Map M. So ignore traversable. They're just lists. Essentially, if I put in an IO function, so a monadic function, so I'm going to put in put strlen. So that takes a string and returns IO nothing. You see the monad is inside the brackets, the list. But if I did that with map M, the monad is outside of the list. And that makes life a lot easier. So that's why we're going to use map M. So let me quickly change that error. Okay. Oh, look. I forgot many things. I also need to return that. Okay, back to where we were. So yes, I've changed it to map M. So X's is a list of monadic values. And that's not great. I'm going to need to go, I'm going to need to do some binding here. I'll call that mx's. F, the type is correct. Oh, there we go. So that should be apply fixed. We'll see. And then we have elab. So here we have in elab. So let's just check that that's the only line that's erroring first. Okay, we have, yeah, we don't care about that. Oh, that's erroring. Okay, so we expected that to error. Why is this erroring? Couldn't match ID value with value. So you have to ask, why is that? So, that is definitely of type value in apply, which means apply must be expecting ID value or something. Let's have a look. Oh, here. Yeah, it is. It is. So I'm going to change this to do notation. That's what I'm going to do. No, that's fair enough. So f prime is going to be eval f in env. And then x's prime, let's get that nice and aligned, is going to be this. And then, so I can get rid of this where. And then this needs, okay, it looks a bit more like what we had before, at least. And apply is monadic, so that should fix that. So yeah, our to-do line and our elab function are now the only errors we have. So let's go and change them. So elab takes an environment, not monadic, a value, not monadic, but then it calls eval here. So we're going to have to make the result monadic. So I'm going to say eval e env. I'm going to bind that to e prime. And then we'll use e prime here. And of course, we need to make the whole thing monadic. So return. Cool. And we're going to have to return this. What I'm going to actually do is, do you remember I skipped a whole bunch of steps last time where I expanded closure args env out? I think I'm going to change that. I think I am. I think it's better to call eval. And the reason for that is once we've made elab monadic, we never need to change it. So I'm going to stick this on a new line, just so I have a bit more space to mess around with it. And I'm going to show you a nice little trick. So if I say L at here, what that means is I've pattern matched. I can use E or args, that's fine. But if I want to refer to the whole thing, I can just call L. That's quite nice. So what I'm going to do is I'm going to eval L. So I'm not actually going to use args or E. The only reason I'm pattern matching is because I need it to be a lambda. And if not, it'll go to the error. So I can kind of ignore these. So I might as well ignore them, I think. So I eval L in an environment, and that environment is env prime. And then I'm going to use that so I'm going to call that, I've got to do some binding. Have I used E prime yet? Nope. E prime it is. E prime, E prime. So I'm evaluating the lambda, sticking it in E prime. And I'm using env prime. So it's still recursive. Also, this is now monadic because I need to, do I need to do, I put an eval here. I don't think I mean eval. Oh, I'm getting myself confused now. I think I just need to return this. Return, yeah, okay. We'll see if that's right. Now let's go to this to-do line because this needs changing. That's monadic now. So let's remove that, stick it at the end. Let's get rid of those brackets. So I have my elaborated environment env prime. Actually, I'll leave it like that. The environment comes at the end anyway. Don't need to do any binding. Okay. So inevitably there are errors because I got myself very confused. So we're doing some couldn't matching. Lovely. What's going on? Oh, I see. I think. Yes. Oh. That's not what I wanted. Not a problem though. So I think I might need to do another bind. Env prime. Eval L in env prime. I think that'll work. Sure, maybe. So I thought this might happen. So there are lots of different special monads out there, like monad plus and monad fail. Now, recently, this code would have worked, but the way Haskell undid syntactic sugar was low-key insane. Because it meant that every monad had to have some way of failing. And that isn't particularly mathematical. Haskell likes to be mathematical. That's very implementation detail, you know. So they made a new monad fail, where you have to provide a fail definition. And maybe we'll do that later. But I don't really want to do that now. I don't want to turn that monad into a failure monad, because I think that is too much implementation detail for this tutorial, and you can look into it because it is a good idea. But we can kind of get the old behavior if we stick some curly boys, I don't know what they're called. So the reason that's happening is because we're pattern matching on this side of the arrow. And yeah, that might fix it. Yes, there we go, fixed. So let's see if it works. I'm just picking up. I don't want to rewrite that huge thing there. I think if you remember, yeah, eval result equals eval, and then I want e, and then so I defined this sum last time, this recursive sum that summed numbers up to another number. So in here we have apply var sum, and we're going to give it number 3. Oh dear. I think I must have made a mistake somewhere. Oh, it's the normal mistake I make. I forget that it expects a list of inputs. What's this now? Oh, this annoys me so much at this point. Did I get rid of? I got rid of at least one of those errors. Couldn't match expected type list to T, actual type ID value. Did I forget things here? No, that was fine. Apply var sum. What's going on here? Ah, there we go. Right. Second type of eval, namely. Ah, that's not going to help. There we go. It was a bracket problem. Oh, so the type of result is going to be m value. Now, what I didn't do was say that ID monad is showable. So I'm going to say ID r. It's going to pattern match it manually. Results, and then we have an infinite loop. Oh, why does this happen? You see, if I said, I know why that's happening actually, but if I just said plus number 1, number 2, and then I said eval e in nothing, I said ID r equals that, and then I said r, that's going to work. So where that mistake has happened, why we got an infinite loop, was because the environment, I think, let me check the code, but I think it was because of our recursive environment. Because I check to see if n equals number 1, n is 0. So I don't think that's the problem. The function seems right to me. Let's have a look. I think this was our problem here. I'm going to do what I did before, which is not use eval. And I'm going to do it like this. Or should I? No. I am going to do it the way. Let's have a look. If I do it like eval L in E n prime, and then, or should I make this pure? Big questions. Yes, I'm going to do it like that. I'm going to not use a val here. IDs and E. I'm going to do it the good old-fashioned way. So that would be closure. Closure, IDs, E, env, prime. Yep. Let's do it that way. Oh. I put the result in the wrong place. Oh, not result, return. Yeah, we used results when I learnt this, and we didn't use proper monads, so sometimes I'll use result when I shouldn't. Okay, that's fine. That's fine. Let's try the example again. Where's that big... That one. Cool. And then... Oh, my terminal can be a bit annoying sometimes. Doing it again. Cool. And then... So that's what we typed, just in case you wondered. Because for some reason I had this frozen thing here. So we have result of type m value, and then we can go id r equals result, and then r6. There we go. The problem was we were forcing the evaluation of env each time, and of course env is an infinite list, kind of, if you do enough forcing. So it was getting stuck. Anyway, now we have a monadic interpreter. I can kind of show you the point, and that's what sort of feature do we think we're missing? And we think of a monad, we change just the bits we need to change, and we change the type. So let's use either for error handling. So what I'm going to say is I'm going to say type MA is either string. So that's going to be an error message, or it's A. And now, there we go. Nothing went wrong. I changed the type and nothing went wrong, and now I can use either. That's kind of the point. So let's have a look. Where did I have errors? Here's an error. I'm not going to have an error anymore. I'm just going to say left. I'm not going to have an error here either. I'm going to say left. And now, so let's have a look. Which of these? So that should compile. Yep. Perfect. I could also use left and right here. Actually, I wonder if that will, out of interest, I'm just going to see if there's a monad fail for, I wonder if there is. No, but I can do that quite easily. So if I go info monad fail, it tells me everything. So I just need to give it a string. Oh, that's nice and easy. So what I'm going to say, I am going to do monad fail, look at me. Instance monad fail of either string, where fail, which was of type string to MA, that is going to be of type, fail just equals left. Oh, so now, let's have a look. Oh, I didn't actually read that. Let me read it. Illegal instance declaration of monad fail either string. All instance must be of the form. Ooh, maybe it wasn't as easy as I thought. Let's try flexible instances. Let's try enabling this language extension. Let's do what it says. Sometimes when things don't work in Haskell, you just do what it says. Language, flexible instances. And then we have to restart the REPL. Use flexible flexible, did I not? Let's go set -x flexible instances as well. There we go. I had to set it in the interpreter as well. GHCI. Great. So what we did then, out of interest, will it come back? No, good. We've got rid of the error for good. So what we've done now is we've removed all of the error messages and we've added it into our type. So instead of our eval function just erroring out, now we have, instead of right and then the answer, we have left and then an error. So let's see if we can get one of these to trigger. I think it's very easy to do here. So all I need to do is I need to do a rec with something that isn't a rec. So a var, I think. So defins val, okay. So if I go let rec, no, what am I doing? Hold on. It's very difficult to work out how to use your interpreter wrong. So the expression needs to not be a lambda. Okay. Let's do this. Let rec, no, e equals let, and then it's going to be rec, and then I'm going to give it an identity of foo, and then the expression is just going to be numval 42 in, and then it's going to be, so what's our in? It's just going to be varfoo. And why did it error? Couldn't match expected expression type with value. So rec has an ident and then an expression, and let has a defin and then an expression. I wonder what error I've made. So let, correct. So then the first thing it has is a defin, and the second thing it has is an expression. And var is definitely an expression. Var ident is an expression. Numval, number. There we go. So if I eval e in the empty environment, it says only lambdas can be recursive. There we go. Now if I change that to eval, if I give it some proper code, it then gives right and then the answer. So isn't that cool? We've managed to use monads now to add proper type level error handling to our, or typed error handling, I should say, not type level error handling, to our interpreter. And we can go crazy with this. So how about the state monad? Yeah, that's a good one. That's a good one. So what if we wanted to add variables? We kind of have variables, but we don't have changeable variables. We have values, basically. Var is a misleading name. What we could add to our interpreter is sort of creating a new memory, place in memory, like on the heap, like new in C. And then we could have that value change. We could, between functions, if we leave the environment if we go into a different environment, say we come out of a function call, that reference in memory will not have changed. So, proper imperative programming language here. The way we do that is with the state monad. Or should I do that next time? I think I'll do that next time, because I think this video is getting a bit long. So next time I will cover the state monad and how we can add variables to our interpreter and make it more imperative in that respect. I'll also cover next time monad transformers, how we can kind of stack up monads. There's a reason I've not deleted this identity monad code. There is a reason, and that's for when we start to use monad transformers. So I'm going to teach you that as well. So by the end of next lesson, you should be able to think about how you can add features to your compiler and how, this way, the type way, changing as little code as possible, keeping everything strongly typed, and how you do that through monad transformers. And after that, I'm going to do parsing and lexing, because I think we can all agree that typing your code out like this is a joke. We should be able to turn strings into expressions. We should be able to, and I'm going to go over, I think, the easiest way, which is using Alex and Happy to do that. Cool. So that's all for this week. See you next week.